Atomic spectroscopy. So when atoms or molecules absorb energy, that energy is often emitted as light energy. Examples of this are fireworks and neon lights, fluorescent lights as well. What's going on with fireworks? You know, they shoot them up in the air and they explode, right? And we see all these colors. Those colors are because the explosion has given energy to the atoms, and then that energy is then released as light. Neon lights, you have a glass tube with neon gas in it, and you pass a current through it, and it glows bright orange. So you're putting energy into the neon gas, and it's giving off light energy. If we take that light that's given off by these elements and pass it through a prism, instead of seeing a continuous rainbow like we see with sunlight, we see lines instead. And that's called an emission spectrum, because it's the emission of light from an atom or a molecule. And so it's an emission spectrum. It's not continuous. It gives us almost a fingerprint of the element, and it can actually be used to identify the element. Classical physics cannot explain what's going on here. So here's 3 lamps. These, and we're gonna be looking at these lamps on Wednesday. This is a mercury lamp, so it's got mercury gas in it, and then we apply voltage across it. This is helium, and this is hydrogen. And each of these lamps emits light of a different color. Oh, that's nice. We see this with flame tests as well. When we put sodium in a flame, or potassium, lithium, barium, we see that the flame turns different colors. And that has to do with the emission of light from these atoms when they absorb energy. So if we take the hydrogen lamp, and we pass the light through a slit just to get rid of some of the scattered light, and then pass it through a prism, what we see is, instead of a rainbow, we see several lines of different colors. They are in the same position here. This orangish line is where orange would be if we were doing this with white light from the sun. And here's blue, kind of a blue-green, and then there's more of an indigo and a violet line. And so these the lights, running out of words. The light is separated in the same way that white light is, but not all the wavelengths are present. There's only particular wavelengths present, and that's why we see discrete lines instead of a continuous spectrum. So here we have the emission spectra for several different things. Here's for helium, barium. This is what we get with white light. We see a continuous rainbow. Here's oxygen, and here's neon. Neon is much more complicated than, say, helium. Any questions? Yeah.
It's because the noble gases expose more electrons in their outer shell.
It's because neon has more electrons.
Right.
So if we look at this, here's neon has 10 electrons, oxygen has 8. So because there are more electrons, there's more possibility for different transitions. And then you might say, well, what about barium? Barium's bigger than any of those. But it's not more complicated than neon. Not all of the energy that's radiated from these things is within the visible spectrum. Here we have emission versus absorption. So emission spectra show bars of light that's emitted. An absorption spectrum is like the reverse. It's like a negative. And so we shine light on it, and we look at what gets absorbed by the substance. And we see that the absorption corresponds to what is emitted when it's excited. So this guy, Johannes Rydberg, looked at a whole bunch of different atomic spectra. He's trying to find out, well, what's going on? What's the relationship between all these lines? And he found that you can describe them with an equation that involves an inverse square of integers. I can't even imagine all the different things he tried. But this is what he came up with. 1 over the wavelength of that light is equal to some constant times 1 over m squared minus 1 over n squared, where n and m are integers. So awesome, he described this, but this doesn't tell us what's going on or why. It doesn't tell us why the atomic spectra are discrete, why it has individual lines. It doesn't tell us why atoms are stable. It doesn't tell why the equation works. It's in essence, it's more of a law. It says, well, this is what happens. I can say all of these, they fit this pattern. Well, let's look at Rutherford's nuclear model of the atom. So we talked about Rutherford's gold foil experiment, didn't we? And so we've got this nucleus, tiny, dense center where almost all the mass is, and the nucleus is positively charged, and we've got the amount of positive charge in the nucleus is balanced by the negative charge of the electrons, and the electrons are moving around in this empty space outside of the nucleus. Okay, so this is, we can get our minds around this. The big question is, what are those electrons doing in that empty space? So electrons are moving charged particles in Rutherford's model. Well, according to classical physics, moving charged particles give off energy. Well, if they're giving off energy constantly, we might expect that the atom is glowing, is giving off energy all the time. And where was this energy coming from that they're giving off all the time? Charged particles moving tell us that the electrons will eventually run out of energy, crash into the nucleus, and the atom should collapse. But it doesn't. So these are problems with Rutherford's model. So that nuclear model doesn't explain the structural changes that occur when an atom gains or loses energy. So along comes Niels Bohr. He developed a model of the atom that helps us to understand what's going on when an atom absorbs energy and why it gives off these discrete emission spectra. So the big idea here is that the energy of the atom is quantized, and that the amount of energy in the atom is related to the electron's position in the atom. So quantized means that there are only specific allowed levels. There are a lot of things in our lives, everyday lives, that are quantized. A set of stairs is quantized. You can be on the first step, you can stand on the second step. You can't hover in between the steps, right? But a ramp is not quantized. A ramp, you could be 1 foot above the ground, you could be 1 foot 1 inch, 1 foot 2 inches, 1 foot 3 inches. You could be anywhere. But on a set of stairs, you could be, if they're 1 foot steps, you could be at 1 foot or 2 feet, you can't be in between. Our monetary system is quantized. There's $1 bills, and there's $2 bills, and there's $5 bills. You can't find a $3.71 bill, right? The coins are quantized. Grades in school are quantized. First grade, second grade, third grade. There's no 2.5 grade. Keys on the piano keyboard. You can play C or you can play C sharp. You can't make a note in between. A violin is not quantized. And that's why you can make such horrendous sounds with a violin. And I played violin when I was a child. I'm not sure, I probably should apologize to my parents, but you can make horrible sounds because you can play in between the notes. Guitars are quantized. They have the fret. You put your finger down, the string touches the fret, and that controls the note. You can play different notes, C sharp, but you can't play in between. So that's quantized. Bohr's idea was that the energy of the atom is quantized. So in the Bohr model, which is by far the easiest model to understand, we have the electrons traveling in orbits, like the planets go in orbits around the sun. And these are stationary states. They're, a spherical orbit, and they're at fixed distances from the nucleus. And the energy of each orbit is quantized, just like stairs or rungs on a ladder. And the electrons will emit radiation when they jump from an orbit with a higher energy to an orbit with a lower energy. That energy has to go somewhere. It gets spit out as a photon of light. The distance in energy between the orbits determines the amount of energy that's emitted. The electron is never observed between states. It's only observed in one state or another. It can be an energy level 2 or an energy level 1, but it can't be in between. And this is the idea of a quantum leap. It does not travel in space between the two levels. It's in one or the other. So the energy, the photon that gets emitted from this atom who's got an electron going from a high level to a low level, the energy of the photon corresponds to the energy difference between those two orbits of the electron. And we can actually do calculations and measure these things because we can see the wavelength of light. We can separate the light based on its wavelength, and from the wavelength, we can measure the energy of the light that's observed. So each of those lines is reflected as, or is reflecting a transition from one state to another within the atom. Really awesome. And the Bohr model works great for hydrogen and nothing else. But it was a breakthrough. It was huge. Here's an illustration. So here we have the nucleus, and here we have energy level 1 and 2 and 3 and 4 and 5. These are orbits, and so the electron is zinging around in here and zinging around in here. And the farther out you get, the higher energy that electron is. So if we have the electron in energy level 5, and it jumps quantum leap from n equals 5 down to n equals 2, this is a lower energy level. It lost energy. The energy has to go somewhere. It's emitted as a photon of light with a wavelength of 434 nanometers, which we perceive as violet. So we can calculate, based on the wavelength of the light that's emitted, we can calculate the difference between these energy levels. It's like so awesome. Any questions? This is about where a student in one of my classes raised his hand and asked how much telescopes cost. I was talking about planets, and he just like tangentially went off in this other direction. Couldn't even answer him. I was so just, what?
So you think if an electron from a higher energy orbit goes towards the center of the nucleus, you're giving off more photon energy.
It'll give off a photon with higher energy.
Great.
So each electron.
Frequency of energy, right? So
Yeah. So the difference in energy between n equals 5 and n equals 2 is greater than n equals 3 and n equals 2. So this is going to be low energy, and this is higher energy.
that distance of the lower energy field give off a lower amplitude, a lower rate of.
It'll be a lower energy photon. You get one photon for each electron moving, doing a leap from one level to another. Yes.
On the previous,
On that one?
I don't know how many slides behind. Helium was giving off like all kinds of different colors,
Right.
but there's only like one or How many orbits does it have?
So here's helium. I'm seeing 1, 2, 3, 4, 5, 6. 6 lines in the visible spectra. So helium has 2 electrons.
We're in the first.
They're in the first energy level in the ground state, and that's kind of getting ahead, if that doesn't make any sense to you. But then there's different possible transitions that they can have. These higher orbits, higher energy orbits, are there whether they are occupied or not.
Oh. So when you put the energy into them, they jump to the next.
Right.
Okay, I get it.
So, you know, this is for hydrogen. Hydrogen only has 1 electron. And normally that electron would be found in the lowest energy level. How does it get up here? It has to absorb energy of some kind. And so in the absorption spectrum, that's what we're observing. We shine light of all these different wavelengths on it, and we observe that it will absorb this wavelength when it does this transition from N2 to N5. It'll absorb this one, it'll absorb that one. Now there are other transitions here, but those energy differences might not fall within the visible spectra. And so we can't actually see them. We only see the ones that are visible. Yes?
So how do they observe that? Do they just do that mathematically or absorb the change from N1 to, say, N5?
There's math involved. Yeah. How you know, what would it be from N equals 1 to N equals 5? I think that's what you're asking, right?
Yeah.
And how would you observe that if it's not visible?
Right.
This is where the Rydberg equation comes in.
Okay.
And so you can calculate any of the possible transitions based on the Rydberg equation, even if they're not within the visible range. How do you prove something you can't see? Well, it works for everything that we can see. And some of these, they have probably come up, you know, they can probably measure them. It's just not as simple as measuring the visible.
We can measure things that are outside our physical spectrum anyways.
Right. And what we're going to do in lab is we're going to use a very, very simple spectroscope that has a little prism in it and a grid, and it'll separate. And just based on the colors and the positions, we'll be able to measure some really cool stuff about atoms. So any other questions about this?